Okay, hello everyone. Good good evening. Yeah, just a moment. Yeah, okay. So let me share my screen. Okay, how many of you have gone through week four's content? Let me training also. Okay, Jalaj. Others, have you? Okay, okay. All right. Okay, I hope you can see the screen. All right, so yeah, this week is about fine tuning, right? In the first week, you did data sets. In the second week, you did tokenizers. In the third week, you did training a model. So basically, that was pre training. Now, in this week, what we're going to do is fine tuning. Fine tuning can be done in different ways. Let me write this down. So we'll see several ways for fine tuning. The first thing that we'll see is low rank adaptation, and then we'll see QLoRa, which is quantized low rank adaptation, and there's also another one which is prefix tuning. Okay, so these three are different ways to do fine tuning, which means we already have a pre-trained model and we want to fine tune the model for a specific problem using a specific data set, which will be a supervised data set, right? In the pre-training, we used self-supervised learning, whereas in fine-tuning, we'll be using a supervised data set where there'll be uh, some data and there'll be a label for that. So that's the kind of data set that we have to use. Let's start off with LoRa. We would need a few, we would need to install a few packages. Okay, I hope I get the GPU. I'll check that. Transformers, we would need. Let's also install Torch. We would need some data set. So I'll install data sets. In order to do fine tuning, we would need PEFT, parameter efficient fine tuning. So let me see if I can get the GPU. Minus U I've written so that we get the updated versions just in case some code I already ran here to install something. I would want that particular library to be, that particular package to be updated. Okay, one more we might need for quantization. Okay, let this get done. So after this, we would need bits and bytes. Bits and bytes is a package that we would need for quantization. This will take, I think, a few more seconds. All right, let this get done. Once these things are installed, let's start importing. Let's start off with Torch, and then we would need transformers. Transformers. There's also some dependency of whenever we load some model, there's some dependency with Torch Vision. So let me import Torch Vision also, just to avoid any errors. And after this, we'll need to load the model. So for that, from transformers, we would need auto model for sequence classification. Let's say we want to load BERT model, BERT base uncased. That model we will load, and we will fine tune that model. So so we want to do sequence classification. So I'll import auto model for sequence classification, AMFSC capital. Okay. All right. So this is taking some time. Okay. So once that will be done, we would need to load the model. So from auto model for sequence classification, we'll load our BERT model. Dot from pre-trained. Okay. We need BERT base uncased. Let's go with this one. We would specify the number of labels to be 2 because we want to go for binary classification. So let's let's do the sentiment classification using IMDb dataset. So I'm going to be downloading the IMDb dataset, which is for sentiment analysis. So we would need 2 labels for that. Some dependency issue. Okay, let's see. Let's see. Okay. This Torch Vision creates issues sometimes. Let me get the latest version of that also. Okay, so that dependency is taken care of. So this is the model that is getting loaded. While this is getting done, we would also need the corresponding tokenizer for the same model. So let us load the tokenizer also from transformers. From pre-trained, the same one. Let's call it tokenizer. So this is the tokenizer that we would be using on the data set, the supervised data set, using which we are going to fine tune our model using LoRa. So let's load the data set now from datasets. So I'm going to download the IMDb dataset. Now, if I take the entire dataset, that is going to take time. So let me start off with a subset of the data. So I'll mention split is equal to train, but in that also I will take only a few samples. So let's say I'll take only first 1,000 samples from the training dataset for fine tuning the model. This, let me call the dataset using which I will fine tune. In case we want to later on test our fine tuned model also, we would need test data set for that. So let me load that also, because the same kind of tokenization will apply to that also. So let me load that now itself. Again, I'll go with 1,000 samples. Okay, so this data set is what we will use for training, for fine tuning. So if you see the first sample, it's like this. It's a dictionary kind, and we have two keys. One is text and the other is label. This is the text of the first one, and then this is the label. Okay, but there's one catch here. Yeah, I shouldn't have actually taken the first 1,000 ones. You know why? So if you see the labels of these first 1,000, so this will be imbalanced actually. So let me see that. If you see the first 5, let's say, let me print the text and the label. So actually IMDb dataset is balanced. The total full dataset is balanced, but when you take the subset, right, that is like I think first 50% samples are negative, 0 for negative here, and the remaining 50% are positive. So I think this is not a good idea to actually take first 1,000 samples. Right, let me just cross check once again. Let me not print this. I'll just see the label for, let's say, for first 50. So the label for all 50 is actually coming out to be 0. That's how this IMDb dataset has been stored. A better idea will be.
Can't you shuffle them and then?
Yeah, that's what. Yeah, we will be shuffling. So, okay, it's asking us to use GPU. We'll soon use that. Okay, so so let's do one thing. Let's take the entire train data set and then shuffle it. So I was just I wanted to save memory because it can crash if we use a heavy data set. Anyway, I think this much will be okay. Now we have taken the entire training data set and then we have shuffled it, and then out of that we will choose how many ever we want. Let's say we'll go ahead with 1,000. So okay, the same should be done with test also. Let me just quickly do that. Okay. Okay, now let's check this. All right, this is fine. So this is a mix of positive and negative samples. All right, so we got the data. Now let's tokenize it. We have already loaded the tokenizer, right? We would need to use the map function. For the map function, we would need a function, right? So that we can pass to that dataset.map. Let's call it something. Let's say tokenize function. We'll pass to our data to it, and what it should do is it should apply the tokenizer. This tokenizer we just now created. Out of these examples, what we need is the text. That is what should be tokenized. Let us do the padding with max length if they are shorter. If the samples are shorter than max length, then padding will be added. And if they are longer, truncation. If they're longer than max length, then they should be truncated. Max length also we can pass. Let's say 512. One more, which is useful, return tensors. Otherwise, if you don't have tensors in PyTorch format, later on when you do the training, then it expects them to be in PyTorch format. So let me convert them already in PyTorch format. Return tensors is equal to pt. This function we have created will apply it to our data set using the map function. This function will pass, and we'll do it in bash manner to speed up. And let's call it tokenized dataset. Tokenized dataset. Okay.
And there is a typo in max length.
Right. Thanks. Okay, so this is our training data set, which we are tokenizing. Similarly, we should also tokenize a test data set in case we want to use that. Let me do that also right now. Let me call it tokenized test data set, test data set.map. Everything else remains same. Okay, so we have tokenized our data. Now we have to fine-tune our model using this data, using LoRa, low rank adaptation. Now there are several things that we would need to apply LoRa, which will come from the library PEFT. PEFT for parameter efficient fine-tuning. What we would need to implement LoRa from this library is LoRa config. LoRa config is a class using which we will define the configuration parameters for low rank adaptation. So this is one thing that we would need. Then to convert our model to a PEFT model, we would need to use a function get PEFT model. So this is the second thing that we would need. We would need to pass a parameter when we create the configuration using this tasks type. So this will be used to mention what kind of task we want to perform. We want to do sequence classification or any other kind of task that we would need to mention here. Question answering can be another kind of task. So in this case, we are going to use sequence classification. So that is the task that we will mention using this task type. Okay, so the first thing is we have to make use of this class to mention the configuration for LoRa. Okay. As we know, what low rank adaptation does is it will create new matrices, two new matrices A and B with a particular rank. So the first thing that we need is the rank of these matrices. We can try out different values here. Let's go with a rank of 8. The other parameter associated with LoRa is alpha, which is called LoRa alpha over here. So this is basically a scaling factor for LoRa weights. So there's some formula, you can just see the approach. So these matrices, right? So they are low ranked matrices. So in order to balance their effect, so if you want to increase, so there are some parameters already which are pre-trained, I mean, which are learned during pre-training, and now the parameters will be learned through LoRa also, right? And then they are added up. Their values are added up, as you know. Now, whose effect you want to be more? To control that that particular effect of LoRa, if you want to increase it, if you want to decrease it, the effect of LoRa matrices, the values that LoRa matrices have, whether you want to increase their effect or decrease their effect, to control that we have this LoRa alpha. So you divide the weights by LoRa alpha, basically. Whatever weights you learn in A and B, divide them by this parameter. So let's go with the value of 16. This is basically scaling factor. Okay. Then if you if you want to avoid overfitting through whatever weights you will learn through LoRa, for that there's a LoRa dropout. The same function, whatever dropout has for handling overfitting, the same thing will happen here in case you want to avoid overfitting. See, the model has learned something already, right, during pre-training. Now, we don't want to deviate much from that during fine-tuning, right? So, we would not want the effect of LoRa matrices to be too much also, right? So, for that purpose, we have these parameters, LoRa alpha and LoRa dropout. Then, what kind of task you want to apply? Now for this, we would need this task type that we have already imported. Now there are several values that you can pass here. In our case, sequence classification. So this is what we will pass, the task type. So this is the LoRa configuration that we are going to use. This LoRa configuration has to be passed to this function, getPEFT model. Now, given a model which is not fine-tuned yet, it will convert that model to a PEFT model. So the parameters are going to be that model which we want to fine-tune, and the second parameter is going to be the configuration that we have just now created. So this is going to be our PEFT model, the LoRa model, which is going to be fine-tuned. Okay, so we haven't done any training so far, any fine-tuning so far. So whenever we have to do either pre-training or fine-tuning, we would need two things from transformers. We would need training arguments and trainer. This is something that you have already used. Training arguments and trainer. Training, as the name indicates, training arguments is a class that is used to pass on what arguments, what parameters of training we want. So this largely, this affects the training in several ways. The values of the parameters that we pass in this class, they control the training. So how much memory is going to be used, how much time it will take for fine tuning, all that depends on what values we pass here in these parameters. Once we have the training arguments, we'll pass that to trainer and we'll start the training or fine tuning. Okay. So these two are needed for both pre-training as well as fine tuning. So let's first create an object of this. Now there are several things that we can pass over here. We can actually skip them also if we don't want to pass, because in that case the default values will be used. But one thing that it expects you to pass is the output directory where it will store the results. There is no default value for this, so it will expect you to pass something here. The rest of the parameters, if you don't pass, it's okay, it will take the default values. Let's pass something here. So this class actually has a lot of parameters. If you see the documentation, a lot of parameters. Let's talk about the most important ones. Evaluation strategy. So it's the same effect as that you would have done with sklearn cross validation, right? You want to keep evaluating your model on the validation data set, whether you want to do that or not. For now, to save memory and time, I'll say no for now. The other parameter is learning rate. Generally, for fine tuning, we keep a low learning rate, and generally for retraining, we keep a high learning rate. The reason you might know that in fine tuning, we don't want to completely change the existing parameters that the model has learned by going through pre-training for such long hours. We don't want to change them a lot. So we generally pass small values here, 10 to the minus 5. So generally, 10 to the minus 5 or 2 into 10 to the minus 5. So generally, it varies from 1e to minus 5 to 5e to minus 5. These are the general values that are passed here. Now, this is something important. Per device train batch size. This affects how much time and memory the tuning will take. Per device train batch size. Let me mention 8 here. So as you know, batch size is an important thing during training. So batch size, as you know, you might know, difference between gradient descent and stochastic gradient descent and mini batch gradient descent. So if you increase the batch size, then obviously the amount of memory would increase, right? So you have a limited memory here. Right now, we are not using a lot of memory. Of course, during training, we would use a lot of that. So if you have a high value here, of course, the training time will reduce, the fine tuning time will reduce, right? If you have a lot of memory with you, then you can increase this value. But if you have a very small amount of memory, then you can either go with 4 also over here, okay? Right, because all these samples will, the number of 8 samples in each batch you will keep before you make any update. So that much memory you should have. Then, okay, generally you can increase the test batch size, because during testing you don't really calculate the gradients, right? So it's not necessary that you will keep these two values to be equal. You can keep test batch size to be greater than train batch size. That is sometimes okay, because during training there are gradients also to be stored, which is not to be done during testing. Okay, then how many epochs you want to run your training for? Again, generally for during fine tuning, it's kept to be small. One moment. During fine tuning, we don't run a lot of epochs. That's not needed. So I'll keep it 2 for now. I'll keep 2 because we have a limited time and and memory. So I'll keep it 2. I will run for 2 epochs. Okay. So what other parameters? So rest of the parameters you can actually go with default, but let me. So weight decay is for overfitting, right? For handling overfitting, L2 regularization it will use. And then if you want to use you want to store the log the results, then that also you can mention. All right, and I think that's okay. Okay, and let's say I don't want to report to WNB for now, so I'll pass a none over there. I don't want to do that logging over there right now. You can also mention logging steps. After how many iterations you want the results to be logged. This again you can vary. If you want fine-grained details, you can have a small value. If you're okay with 100, you can mention a higher value, 100 or 1000 or so. Okay, so these are some parameters per device test batch size. Sorry, this is not test. This is eval for evaluation. Okay, so these are the training arguments. And the next thing that we need is trainer. So we have to create a trainer, an instance of trainer.
Ma'am, can I ask a question?
Yeah, sure.
Could you just please explain the learning rate criteria once again? How do you say? Yeah.
Okay, so learning rate is basically the same that you have already known about in gradient descent, right? This is basically the step size, right?
Yeah, that is clear. So how you said something about selecting a low learning rate?
Yeah. So generally for fine tuning, we keep learning rate to be small because we don't want the model to become inconsistent. So what happens if you have a high learning rate?
Right.
It can actually surpass the minima, right? So right. So if you keep a very high learning rate, the changes made to the weights will be high, right?
Yes, ma'am.
So here, this is fine tuning. So most of the things have been learned already during pre-training. We don't want to change them by very large values, right? We want to only slightly tweak them to understand what is there in our small supervised data set on which we are fine tuning. So generally, we keep small values here. I was saying that generally we keep 1e minus 5 to 5e minus 5. Those kind of values we keep. I don't know. I think by default it's 2e minus 5 or 3e minus 5. Okay, so such values we generally keep during fine tuning, and during pre-training we generally keep higher values. I don't know what you used in what you did in week 3. You could have higher values over there during pre-training. Yeah.
Okay.
Okay. Okay. One more thing I think I should tell you. Gradient accumulation steps. Gradient accumulation steps. I think it will expect Boolean value. So gradient accumulation steps. This is something you should know about. It has an effect of a larger batch size actually. So what it does is it will keep accumulating the gradients across multiple iterations, and then it will make an update. So let's say we have a batch size of 8, right? So, and we say that it should accumulate the gradients. I think there should be one more parameter which should mention how many steps should be accumulated. I'll check that. I think there should be one more parameter which should say how many steps gradient should be accumulated. So when batch size is 8, 8 samples will be there in one batch, and after that the weights will be updated, right? When gradient accumulation steps is true, I think by default it is false. So this actually speeds up. So it's a good idea to keep it to be a true value. maybe there's some fixed number of steps after which the weight update actually happens. Before that, the gradients keep getting accumulated. So if you want to speed up things, you should keep this value to be true. Okay, and there's something FP also. There's one more parameter, FP16. So this is floating point 16. So generally 32 bits are used, right? So this parameter also leads to lesser memory usage. Well, this is different from quantization, which we'll do later. But this parameter also, if you're using GPUs, then this so 32 bits floating point numbers will be converted to 16 bits. So there'll be some loss of precision, but that's okay. If you want to have speed up in memory, if you want to conserve memory, then you can keep this to be true. This T4 that we're using, this is also dependent on the GPU that we are using. NVIDIA T4 that we are currently using from this Colab, that supports FP16. There are a couple of other ones. For example, TF32 is also there. TF32 is not supported by this GPU T4. TF32 is used for transformer, TensorFlow based GPUs. For this GPU, FP16 will be helpful. So let me go ahead with that here.
Ma'am, one question.
Yeah.
So how does the gradient accumulation steps work for a batch size of 1?
Yeah, so batch size 1 means it's basically one sample, right? After each sample, you are updating weights, correct? That's clear?
Yeah, ma'am.
Now, gradient accumulation steps, I'll have to check after how many steps the gradient is, the weights are updated. The gradients are accumulated for those many steps. There'll be some parameter which will contain the default value of this number of steps. Let's say 4. Okay. Now, if that default value of steps is 4, then, well, in this case, the batch size is 8. So 8 into 4 is 32. So this will have an effect of a batch size of 32. Is this clear? So let me repeat. So batch size is 8. Let's say you use this to be true, and the default value of number of steps is 4. So after 4 steps, which in case will be 8 plus 8 plus 8 plus 8, which is 32 samples. So after seeing 32 samples, the weights will be updated. So that has an effect of batch size being 32. But here in this case, we will not go with the batch size of 32 because we don't have a lot of memory. Okay, but then if you use this parameter, gradient accumulation steps, to be true, that will have an effect of batch size to be 32. Now getting back to your question, if batch size is 1 and this we are keeping true, and let's say steps is 4, then that will have an effect of batch size to be 4. Now, even if you have lesser amount of memory and hence you had kept the batch size to be 1, you will have an effect same as batch size to be 4.
Yeah,
is this
okay.
making sense to you?
Yeah, it makes sense, because if you have less amount of memory, then the way to optimize your training
Right.
is to actually set this gradient accumulation steps to true,
Right.
so that even with a lower sample size, you can
Lower batch
I mean,
size.
you can speed up your processing, right?
Yes.
Yeah. Okay.
Okay, so now we have to create an instance of trainer. I think I've told you about most important parameters of training arguments. If there's anything else that comes to mind, I'll tell you. So here, now we have to start the fine tuning using this trainer class object. And obviously what all it will need is which model has to be fine tuned. So model is equal to model. The name of our model was, I think, model itself. Right, the model itself. This is the model that we have to fine tune. So that's the first thing that will pass. Now, what should be the parameters during training that we'll use? The training arguments. And what data set, right? Makes sense. These three things are the most important to actually carry out a fine tuning. So train data set using which this fine tuning should be done, and that is the tokenized data set that we have just now created. Tokenized data set. Using this, we are going to fine tune. So this is just an instance of trainer that got created. No training has happened so far. In order to carry out the training, we'll call this function train through this trainer object. Now this is when the fine tuning will take place, if there is no error. Okay. Less than equal to not supported between instances of float and string. Okay. Some tokenization issue maybe. Invalid learning rate. No, this LR is not here. Learning rate. This is fine. Okay, let me restart this.
So learning rate parameter would
No,
be.
this is not LR. This is a different parameter. This LR. What? We passed a string, is it? No, this is. This we passed string. Okay, I think maybe it is referring to that. This, yeah, correct. It could be possible. Correct. It could be possible. Yeah, this is 10 to the minus 5. You can't pass that as string. You're right. Okay, we'll rerun this. Yeah, we'll run this everything. It won't take that much time. It'll be done quickly. Anyway, yeah, correct. Whoever pointed this out, this is we passed it in codes. That seemed to be an issue probably. Yeah. Okay, while this is getting done, once this reaches at this point, the training will start, and this is going to take a good amount of time. Okay. Now, some number of iterations will take place here, but we passed the number of epochs to be 2, right? But the number of iterations is going to be how many? So we have how many samples? We had 1,000 samples, right? That's we can pass the entire data set also, but right now we are passing 1,000 samples for training, and we are passing a batch size to be 8. Let me see where it has reached. Okay, it's just installing again. Yeah, I should have fixed that and rerun from there, but it's okay. Yeah, so batch size is 8,000 samples. 1,000 divided by 8 is 125, right? Right. So 125, and the number of epochs is 2. So 125 into 2. 250 should be the number of iterations that should take place during training. Okay. Let's see. So we have the GPU. So let's see how much time that will take. On CPU, it takes I think even 1,000 samples will take more than 1.5 hours. But with GPU, it should be a few minutes only. It should be doable right now. Okay, I restarted everything, but it's okay. It'll be done in a few minutes. Never mind. So once this is done, we'll see. We'll see once this fine tuning happens. We can make use of that model, and we can store save also if we want. No. Trainer dot save model. Okay, we can save that using some name, and we can load that whenever needed, right? The way we loaded that BERT base uncased, we can load this also later at any later point of time.
Ma'am, we didn't use the data collator, right? I mean, would you use that only for large data sets?
That you will use for training, as in pre-training. Okay, that you will use for pre-training, because the advantage of using data collator is that it will so let's say you want to use masked language modeling, MLM you want to use. So you want to create masks different places in the given data set, which is not a supervised data set. That's let's say the entire data set of Wikipedia. So there are no labels. You want to fetch that data, some amount of data, one by one you will keep fetching, and you will, with some probability, you will create some masks there, right? So if you want to do that, for that you would need data collator. Here it is not needed.
Okay.
Okay.
Yeah.
Okay. Come on, still doing this. Anyway, so let's continue from here. Let's say our fine tuning has happened. We can test that model. So basically, we can have a sample. So what have we done? We have created a sentiment analyzer, right? So given a sentence, it should be able to tell its sentiment. So let's see how we can do that. By the way, since we are using GPU, so everything should be moved to GPU. I hope you have done all this in PyTorch. I'm just writing this so that, if now that GPU is there, so it will move things as in our model and the sample to GPU. If that is not available, then model and sample will stay on CPU. Let's say we just have a sample for which we want to predict the sentiment. Okay, good. It has reached here. So the fine tuning is happening. All right. So this is what we see. 250. These are the iterations. Iterations as in the number of times the weights are getting updated. Okay. And how we got this 250, I told you, 1000 divided by 8 into 2. 8 is the batch size, 2 is the number of epochs, 1000 is the number of samples. Well, CPU will take so many minutes to even reach from 10 to 20. Okay, you can try that out. If you don't have access to GPU, that will take time. Okay, it's quickly getting done. All right. So the fine tuning has happened. We can save this model. So let us test this model. Please note that this is our sample and it has to be tokenized before we can pass to the model using the same tokenizer. All right. What do we have to tokenize? This thing. Everything else will pass again, truncation and padding and max length, etc. Truncation to be true, padding to be true. Max length we had passed 5 and 2, right? Let me check.
It was 5 and 2, and
Right.
padding was given as max length.
Padding was max length. Let me copy paste this. Yeah. Okay. Okay. Now this is our tokenized sample. We have to move it to whatever device we are using. Right. I hope. Okay. Okay. So now our model and the sample both are on whatever device we are using, which is GPU right now. Model we have to use now. So model.eval, I'll go into the evaluation mode so that gradients are not touched. Also, I can actually use one of these two things. but I'm using both just like that. You can skip any of these two. Okay, both have the same effect, that the gradients will not be updated, calculated. So what the model will return are the values for on which you have to apply the softmax or softmax, right? So what we have to pass here is this test encoding. Let's print also. Let's print what the model is giving us. In this case, it should give us two values, right? This is what it is giving us, right? By the way, we have trained on fine-tune only on 1,000 samples, which is actually a very small number. We should actually tune on a larger data set, right? By the way, I think this is a negative class and this is a positive class. So this is actually giving us a negative result.
But ma'am, in order to fine tune, you need to load the pre-trained model parameters, right? We didn't do that.
And that has happened right here. This when you load this model, the the parameters have come, right?
Okay, got it. Yeah, sorry. Yeah.
Okay, so yeah, so the argmax we are going to apply. Well, we can see that argmax will give us this, which is 0, which is actually negative class, which is bad. You run it on a larger sample, larger data set, and then see the result. Okay, this is not correct. So go back, increase the data set size. And in fact, what you can do is, okay, test data set we have already loaded and we have tokenized that also. So what you can do is you can find the F1 score. Okay, so if you are not happy with the F1 score that you are getting on the test data set, you increase the data set size, and or you can use any other data set. So that all you can do. So for F1 score, I don't think in Hugging Face or PyTorch I've used from sklearn itself. You can continue using that from there, that function basically. Go ahead and calculate this. I'm not going to do it, so I hope you can do that. So if you're okay with the F1 score that you're getting, fine. Otherwise, increase the sample size, that is data set size. Okay, so this all was LoRa, right? I hope the workflow and the libraries that are needed is clear. Next is QLoRa. It's as you can see, it's Q plus LoRa, which means whatever we did in LoRa is going to be done again. So the fine tuning is the same. The only difference that QLoRa brings in is the quantization, which is it reduces the memory requirement, and that is a very important thing that we need, because we have very limited memory when the model is huge, and each parameter, and a lot of parameters are there, and each parameter is taking let's say 4 bytes, 32-bit of memory. The floating point 32-bit memory is being taken by each parameter, and there are so many parameters, and during training or any kind of fine tuning, we would need to store the gradients also. So that will also take an equal amount of memory, and then so many other things that we have to do during forward propagation. All this will take memory. So what if we can reduce that size, that amount of memory? For that, we will use quantization along with LoRa. So whatever we did so far, everything will remain the same. We would see how to bring in the quantization now. Okay. Bits and bytes we have already installed. In the beginning we did. That library is for doing quantization. Now, just like we created a configuration for LoRa, we have to create a configuration for quantization also. And that is done using bits and bytes config. Bits and bytes config. Okay, BABC capital. We are going to use this to create a configuration. Configuration simply means what parameters, basically the specific details of that particular algorithm, right? Be it LoRa, be it quantization. Now, in this case, in case of quantization, what is it that we need? Let's see. Bits and bytes config, let's call it. Now, we can either go with the 4-bit quantization or we can go with an 8-bit quantization. So right now, each parameter is going to take 32 bits, right? We want to reduce that requirement. 32 bits, whatever is taking 32 bits, we want to change their value so that they take the parameters, they take 8-bit, let's say. I'm going to demonstrate 8 bits. You can check out for 4 bits also. So you can see the amount of reduction in memory that is happening. 32-bit is getting reduced to 8 bits, 1/4 reduction, right? So the parameters to mention that will be, first one, load in 8-bit is equal to true. Okay. I want to load the parameters in 8-bit format. Well, I don't know whether you know what happens in quantization or not, but well, to give you the broad idea, let's say that something is 32.56. We will firstly convert the floating point numbers to integers. So there'll be a reduction of memory that will happen there also. So something that is 32.56 getting reduced to 32. There is a very small amount of sorry. There's a very small amount of what did I say? Yeah, some precision loss is happening, but that's okay because the memory is also a very important thing to reduce when we have limited resources. So firstly the precision is going, that's okay. Second thing is so if you ask me the details, right? So at a particular layer, whatever values of parameters that we have, we'll see what is the min range, what is the max range, what is the min value, what is the max value, and then we apply a min max scaling to that, something that you would have done in sklearn, min max scaler, right? So every value gets reduced between 0 to 1. And then if you're using a 4-bit, if you're using 4 bits, then your values can range from 4 bits means 32, and if you're using a positive and negative, so -8 to +7 or -7 to +8, right? These 15 values you can manage. So every layer, whatever parameters values we have, we are going to convert them into these 15 values ranging from -7 to +8 or -8 to +7. These are 15 values which we can manage in a 4-bit range. So basically every value gets converted into a value between -7 to +8, right? Is the big picture clear? So that's a broad idea of quantization. Let me get back here. The other parameters that we would need are, there's one more thing that I should explain to you. So bits and bytes 8-bit use double quant. So this is another thing that you should be aware of. Double quantization. I'm going to set it to true. So what it does is it provides another layer of quantization, and that leads to further reduction in memory. So let me give you the broad idea here. So while we are converting something from 32.56 to whatever value it gets converted to after quantization, how do we get that? We apply some scaling, right? Whatever formula that comes out after min-max scaling, and then multiply by some value, so that the resultant value will be between -7 to +8. In this case, it will be multiplied by 15 minus 8. So then there's some scaling factor that will come in. Now note that these scaling factors also need to be stored, right? And if you're storing those scaling factors in again 32-bit memory, then again you're taking some memory there. So if you want to store the scaling factors also in 4-bit memory, then you apply one more layer of quantization on the scaling factors only. That is what we mean by double quantization, and I'm setting that to true to further save memory. Okay, one more parameter, the data type. The computation happens in which data type? So I am mentioning that the computation should happen in float 16 instead of float 32, which is by default. Okay, so that also leads to 1/2 reduction in memory during computation. One more, which is useful only when you're using multiple GPUs. So there are several tasks to be performed. When you have multiple GPUs, then it will automatically assign those tasks to these multiple GPUs. Okay, and if you want, you can yourself also assign, you can mention that this task should go to this GPU. That detail you can provide, but auto is a good option. It will automatically see which task to assign to which GPU in case you have multiple GPUs. So these are some of the parameters which are needed for quantization. Okay, once we have this BNB config, the only difference that comes in here with respect to LoRa is the following. While you're loading the model, which you did earlier, let me just copy paste that, because we'll just make some change there. This is where we loaded our model, right? I'm going to copy paste this because there are parameters in this model and they have to be quantized. So the moment we are loading the model, at that point itself, we are going to mention that we want quantization. So this will remain the same. These two things will remain the same.
One question, ma'am. So, we haven't loaded the LoRa model yet.
Sorry?
The LoRa model is not. Where is the LoRa model in this version?
In QLoRa, you're asking?
No, the LoRa model, the PFT LoRa.
In this first part we did, right?
Did we use get PFT model?
This thing you're asking, right?
Yeah. Okay. You've done that. Okay,
Did
sorry.
that, right?
Sorry,
Yeah,
I'm not.
No problem.
Yeah, sorry.
No problem. Okay, so yeah, so this so far this is how we loaded the model, and that will remain the same. There's only one extra parameter that we are going to pass: quantization config. Quantization config, right? And this config we have just now created, that's the config that we're going to pass. Quantization, I hope the spellings are correct. Yeah. Okay, I know why it is giving this thing. Anyway, so now while loading the model, this quantization is going to be performed. That is the only change that we will make. If you want to perform QLoRa. And one more thing, sometimes you would see, instead of this BNB config, instead of this very object, you would simply see So let me show you. This is also something that people do. Simply, you don't create create any configuration like we just now did. Simply pass this parameter. This is a parameter load in 8-bit in here as well. So this parameter, we passed here in bits and bytes config, but this parameter is available here also. So you would see in some places that while loading, we're simply mentioning load in 8-bit, that's all. 8-bit quantization will be applied. So, but right now, double quantization is not happening, right? Because if you want to do that, and this, 8-bit compute data type, we are not able to mention. If you want to do that, then go for this entire config object creation and pass that over here. If you don't want that, you simply want one layer of quantization, you go with this. Okay. This was QLoRa, and now the next thing, the last thing is prefix tuning, which is another kind of parameter efficient fine tuning.
Hello.
Any question there?
Yeah.
Yeah, go ahead.
In this, the QLoRa config, we have not used the LoRa config here.
Everything else has to be done. Sorry if I missed that part. So we have loaded our model, right?
Yeah.
Here. After loading, we have to do fine tuning, which we have not done right now, but whatever we did in the first part, that has to be repeated. Are you getting me?
Yeah, I got it.
So, which means we need some data set, we need to tokenize that, we need to create an instance of LoRa, this thing, LoRa config, we need to create get PEF model, we need to create these two things, and then we have to start the training. That will finish. Okay?
Yeah, got it.
Okay. Prefix tuning. The third kind of parameter efficient fine tuning. We would need from PEFT one more thing, which is not one more thing. We won't need LoRa and QLoRa configurations. Now, all that we would need is prefix tuning config, right? So the same way, there'll be a configuration that we will mention for prefix tuning as well. So from PEFT, we would import this. Okay. The model we will load as before as in, do I have that? No. As before as in the beginning, how we had done. This is how, not this thing, quantization. This is how we first load the model. Now we need a configuration for prefix tuning also. Let me call it something. Okay. Now, if you know how prefix tuning works, we need to prefix the tokens, some number of tokens to each layer, and those tokens will have some values. They will be the parameters which are to be fine-tuned during the prefix tuning. So we need to mention how many tokens we want to attach to each layer. They're actually called virtual tokens. They're called virtual tokens. So how many of them we want to add? Let me go with a value of 20. You can vary it. So if you have a lot of tokens added, then that'll take a lot of time, and your original weights will be updated by huge values, right? If you simply want only a small amount of fine tuning to take place, you will have only a small number of tokens added over here. Task type is another thing that needs to be passed here. Sequence classification is what we'll mention. Now, this is the configuration object for prefix tuning. And once again, the way we passed earlier, get PEFT model. Inside this, now we are going to pass. So we want to convert this model to prefix tuning model. So I'll pass the prefix config over here. Okay. Let me call it model. So now this is my updated, not updated, the tuning is, fine tuning is yet to happen, but I've created an instance of prefix tuning, prefix type from get model. Okay. After this, you know what is to be done. You need a data set. You need to tokenize that. You need to create training arguments and trainer. These two things you need to mention. And everything else will go as before. You'll call trainer.train, and that will be prefix tuning for you. Okay. Is this clear? Any doubts? Okay, so this was a broad idea of LoRa, QLoRa, and prefix tuning for you. I think the lecture, the week 4 has also another thing, which is continual pre-training. I hope that is clear to everyone, that is not fine tuning. That is model has been pre-trained already and you want to do some more pre-training, right? That's not fine tuning. That is continual pre-training. And as you know, for pre-training, you don't need a supervised data set. So you will make use of a data set, let's say like Wikipedia, right? Wikitext data set is there on Hugging Face, which is which is not supervised data set. There are no labels, so that data set you can load, and in that case you will need data collator and all these things. Okay. All right, so that was all for today. If you have any doubts, please go ahead. Any doubts? All right, so I hope this was clear. This collab short, Chaitanya, I will share in the supplementary section. By tomorrow, it will be shared. Okay. All right, so I hope that was clear. Please post on Discourse if you have any doubts, any questions later. Okay. Thanks, everyone. Take care. Bye.
Thank you, ma'am.
Thank you, ma'am.